Welcome back to Physics Tutoring from OTS, and in this video we'll be going over average velocity and speed as well as position time graphs later on, which I will put the benchmark and timestamp for if you want to skip to just that. So first, for kinematics, the first topic you usually cover in kinematics is average velocity and the difference between average velocity and average speed and how to calculate each of these. So one motion can split into two honest numbers. So none of these numbers is wrong by itself, right? Velocity is a different quantity and speed is a different quantity. Speed is a scalar, which I covered in my previous videos, and velocity is also a vector, which I covered in my previous videos. But the difference comes in calculating average speed and calculating average velocity. So speed average, which I'm going to denote by SAVG, is the total distance, okay, d tot for d total, over time total. So the average speed is equal to total distance over the total time, which makes sense, right? Speed is not about, how far did you move, it's just how much distance did you cover. And then speed is just the rate of change of the distance you covered, right? So that's it. And displacement or velocity average would be different. It would be displacement over time. So displacement total, so I'm going to write it as di to differentiate it from d for distance, over time total. So since we know that displacement is just the distance between the its final position and the its initial position, we can write it as its final minus its initial over t. Okay, the t is coming from here. And its f just denotes its final. Okay, it's the final its position. So for example, if I started over here at 0 meters and I went over here to 2 meters, then if I stopped over there, my final position would be its f. If I started at 0 meters, my initial position would be its I. And its I is its initial. It's where you start. So velocity average is equal to its f minus its I divided by t. Okay. And let's look at this example through the lens of the track running example that I gave you before. If you run around a track, right, and you end up at the same spot, 400 meters is the distance you traveled. And let's just say you ran it in 55 seconds, which is pretty fast. Or actually, let's just do 50 seconds for the sake of the math. This would give you 8 meters per second, right? That's your speed, because that's your total distance over your time. But if you calculate your average velocity, it would be displacement. Your displacement is 0 meters because you ended at the same place over whatever time, doesn't matter, right? 0 just gives you 0. That's why it's different to track. That's why it's important to track average speed versus average velocity. Now, we'll be looking at one of the most fundamental kinematics equations in this unit. And that's going to be its f is equal to its I plus vt. And I'll show you where this equation comes from. So basically, y is equal to mx plus b, right? B is its initial, because that's the y-intercept, right? Plus mx. The slope is going to be v. X is t. And then y is your its final. So its initial is b because it's the initial position, right? For example, if you started off over here at 0 meters, or actually, let's just say this is 0 meters, this wall, and this is 10 meters. If you moved all the way over here, to 35 meters, then think about it. How could you calculate its final if you didn't know that this was 35 meters, but instead if you knew the velocity and the time? Suppose I told you I was traveling at 5 meters per second for 5 seconds. Okay, so that means we can start here at x final, which we don't know, is equal to v times t, 5 meters per second, times time, which is what? 5 seconds, plus x initial, which is 10 meters. We started at 10 meters. This gives you 25 meters plus 10 meters, or 35 meters. Now the thing is, where is this equation coming from? Does it make sense? It does, right? Because v is how fast you're traveling, and t is how long you do that for. So for example, if you're going 60 miles an hour, then in 1 hour you go 60 miles, right? In 2 hours you go 120. Like that, velocity times time tells you how fast you've traveled per time, which gives you the distance. Okay, how much distance have you traveled? Like, if I was going 2 meters per second for 1 second, that means I went 2 meters. For 2 seconds, that means I went 4 meters, right? Similarly, v times t gives you the amount of distance you travel. Your speed for these many seconds took you this far. And then you just add your initial position, because sometimes you can start somewhere else, right? And then you can go that way. So that's just the basic behind how you got this equation. Pretty neat. Because I don't want to just show you the equation and just expect you to believe it. I'll show you where it comes from as well. And a negative final position is not an error, because you could end up going backward, right? If your velocity was negative, then you could end up at the negative final position if you're going backward. It doesn't need to be always forward. It's just where you end up. So as always, pause the video and try these practice problems. All right, let's work through it together. So we started at xi equals 3 meters. Move v is equal to positive 5 meters per second for 4 seconds. What is xf? xf is equal to xi, which is 3 meters, plus v times t. So 5 meters per second times 4 seconds. Seconds cancel out here, and we're left with x final is equal to 3 meters plus 20 meters, or 23 meters. In this case, we have negative velocity. We start at xi equals 2, move at v equals negative 7 meters per second for 5 seconds. Find xf, then interpret the sign of the resultant words. Okay, so xf is equal to x initial, or 2. We start at 2 meters, and then we move at negative 7 meters per second for 5 seconds. So we move at this rate for 5 seconds. That means we moved negative 35 meters. 2 meters minus negative 35 meters gives us negative 33 meters. Or this means 33 meters to the left of the origin point, or whatever point you call 0 meters. That's what the negative means, the opposite direction of the pod of this 2 meters. Now, a car at negative 15 meters moves at positive 6 meters per second for 8 seconds. Find xf and state whether the car crosses at x equals 0 during the trip. Okay, xf is equal to negative 15 meter is where we start, plus v times t, 6 meters per second, times 8 seconds. Cancel these out. Negative 15 meter plus 48 meter. Or in other words, 33 meters. So we did cross x equals 0, right? Because we went 33 above that. But how? I have another question for you. How would you find the time that you crossed x equals 0? Think about it for a sec. You know that the final position is 0, right? So instead of saying xf, you can say 0 equals. You know, x initial is negative 15 meters plus vt, 6 meters per second, but we don't know the time, which is what we'll figure out, right? I add 15 meters to both these sides, and then I divide that by 6 meters per second, which leaves me with 2.5 seconds. So this equation is not just for finding xf, right? If you need the velocity or the time or x initial, you can use it if you have all the 3 other variables. So as you can see, answers are over here. Now let's go over position time graphs. So position time graphs are exactly what they sound like. The position as a function of time. How far something is or what its position is with the input as how much time has passed. So in this case, you can see, if you remember my rules for Sultan graphing, which I covered in another video, right? Time is over here. I put the units in seconds, S. Distance over here, meters, M. Or you can write position, doesn't need to be distance. Either way works. Okay. Now, you can notice that this is another proof of the equation I showed you, right? HF is equal to H psi plus VT. If you take the slope of this graph, which shows you the distance as a function of time, then what are you going to get? Rise over run. So rise is going to be in what? It's going to be in meters, right? Because delta x is going to be in meters. How far, how much did it change? Not delta x as in delta y over delta x. Delta x is in x position. So that's why I'm just going to write x position or delta distance. So this unit is going to be in meters. And that's going to be over. What's the unit for delta x here? Change in time, right? Which is seconds, because the unit in second. So that's why the velocity is the slope of this graph. Okay, slope of position time graph is your velocity. Why is it not speed? Because speed also has units of meter per second, right? Well, you can think about it as this way. If our graph was going downward, which meant we started one position and then we were going the opposite direction, or negative velocity, then if you took the slope of this, you get a negative slope. But you can't have a negative speed, right? That's why this means velocity, because you can have a direction and a negative value for that. But for speed, you can only have magnitude, which is positive. Okay? Now, we know that the slope is delta s over delta t, which is in meter per second, or velocity. X initial would be our y-intercept over here. So it would be over here, X initial. And v times t, like velocity times t is equal to meter per second times second, right? Or delta y is equal to mx plus b. Same thing here. M is the slope v, x is the t, because it's the independent variable, right? That's being inputted in. So yeah, that's a quick little fun fact, right? You can see how these graphs correlate and how the slope of the graph is velocity. Now let's go over steepness and speed of graphs. The steepness of a graph is correlated directly to its speed. So I told you that the slope of a graph, a position time graph, is velocity, right? Not speed. So why am I talking about speed here? I'm saying that because the slope, the exact slope is a velocity, but how steep it is or how narrow it is it indicates its speed. It indicates its magnitude. Okay? So you can have a negative velocity over here, but if the negative velocity goes like this, sorry, just a little voice crack. If the negative velocity goes like this, then that means it's going faster, right? Because if you look here, for 1 second, if you assume this is 1 second, I covered 3 meters. Even though it's negative 3, I still covered 3 meters, right? But over here for 1 second, I didn't cover even half of that, which means this graph is going way faster and I'm going at a way higher speed, as well as velocity, but this is directly speed because it's not magnitude, right? You can't do negative 3 is lesser than 3. We're not looking at that. We're looking at the absolute value, which is speed. So this graph would be the fastest. Okay, this one would be somewhat fast, not really as much as this one. And flat graphs or zero graphs means it's at rest. It's not moving. Okay, so if I was to draw my schedule for school or anybody's schedule for school, it would probably look like this, right? So let's just say my home is over here. My school is over here. Okay. If I said this is 0 meters and this is 300 meters, if I went here, then that would be positive velocity, right? Because I'm going in the positive x direction. So that's why my slope here would be positive if this was a function of time and distance. Then I would just stay at school, right? I wouldn't move on. I would just stay there and I would just study. So that's a zero graph, or it's flat, which means I'm at rest. I'm not moving. I'm staying there and it makes sense, right? The slope is how fast you're changing. But if you're not changing at all, the slope will be zero. That's what the zero graph means. And this is negative because I come back and I'm going from 300 to 0, right? So it's opposite. I'm going at the, 0 minus 300. That's negative. That's why it's a negative slope, going in the opposite direction. So if you ever forget these meanings, then just understand that. If you look at these points and you're given a question that says find the value of this time or x final at this time, then it's very simple how to do it. First, you have to find the graph of this function, okay? So x initial is going to be 2 because we know that we're starting at 2, right? The y-intercept is x initial. So it's going to be 2 because we started at 2 here. So x final is equal to 2 plus velocity times time. So velocity, how do we find out the velocity? We know that's the slope of this graph. So I'm going to do 20 minus 2 meters over 6 minus 0 seconds. Gives me 3 meters per second. So 2 plus 3 meters per second. Oh, so I should probably put units here as well. 2 meters plus 3 meters per second times time. We don't know what the time is because we can put in any time, right? And then if I asked you to find the distance at t equals 10 seconds, how do you do that? You just plug in x final is equal to 2 meters plus 3 meters per second times 10 seconds. Cancel out these. X final is equal to 2 meters plus 30 meters, or 32 meters. Okay? So you'd have to write out an equation like that for a graph. So this is a practice for velocity, as always, right? More comprehensive and harder questions, something you're more likely to see on the test, you'll be seeing on my OTS website, otslearning.com. I'll have the PDFs up shortly. So make sure to look at those if you need help, okay? Pull velocity and predictions off the graph. A position time graph shows one straight line from 0 seconds, 1 meter to 5 seconds, 16 meters. So something that looks probably like this. Find the velocity from its slope. Well, this is pretty straightforward, right? It's a position time graph, so the slope is its velocity. I find the slope, which should be 16 meters minus 1 meter, y1 minus y2, right? Over 5 seconds minus 0 seconds. This gives me 3 meters per second. That's velocity. Use segments A and B at right. State which represents faster motion and which moves in the negative direction. So since A is steeper, A represents faster motion. So it's not because B is negative. It's just that B is not as steep as it is, as A is. If B was something like this, if I use a different color, if it was something like this, then that means B would be way faster, right? It's just that B is more broad than A is. That's why B is not the faster graph, because the steepness of a graph indicates its slope, or its speed, sorry. So then we know that A is the faster graph. But which one moves in the negative direction? If it has a negative slope, that means it has a negative velocity. Negative velocity means it's moving opposite to the conventional direction. So B would be moving in the negative direction and A would be faster. So given xi is equal to 4 meters and a slope of 2 meters per second, find the position at t equals 9 seconds using xf is equal to xi plus vt. Pretty straightforward, right? X final is equal to x initial, which is 4 meters, plus 2 meters per second. The problem here was you should have known that the slope of a graph equals its velocity. If you knew that, this would be easy peasy for you. And position at t equals 9 seconds. So this gives us 4 meters plus seconds cancel out, 18 meters, which gives us 22 meters. Now that's it for this video. Next video we'll be going over velocity time graphs, area, displacement, and way more about velocity as well as acceleration. So stay tuned and give me a like and follow if you believe I helped your content, if I helped you study. Okay? And yeah, I'll be pushing out the PDFs, which you can work on, and I'll be pushing out a video about how to solve the hardest practice problems or hardest problems regarding kinematics. So have a good day and keep learning.